So, shall we start the session?
I'm ready, my end.
Okay. Good afternoon to one and all. Welcome to the 34th edition of the Kerala Science Congress, organized by Kerala State Council for Science, Technology and Environment. We are about to begin the memorial lectures. The first memorial lecture is Dr. Thanu Padmanabhan Memorial Lecture, being delivered by Dr. P. Sreekumar, former Director, Indian Institute of Astrophysics. To welcome and introduce the speaker, let me invite Dr. K.R. Lekha, Senior Principal Scientist, Kerala State Council for Science, Technology and Environment. Over to you, madam.
Thank you, Arjun Prasad. Am I audible?
Yes.
Yes. Yes.
Distinguished speaker of the day, Dr. P. Sreekumar, Satish Dhawan Professor, ISRO Headquarters, Bangalore. My colleagues, scientists, participants, good afternoon to all of you. As you are aware, the Kerala Science Congress is a proud moment for the entire scientific community of Kerala to come together, discuss, deliberate, and evolve strategies and policies for the development of our nation and our state in particular. In this perspective, the Kerala Science Congress hosts commemorative lectures as a mark of respect towards the doyens who contributed immensely in shaping the science and technology sector in our state. Today we have Dr. Thanu Padmanabhan Memorial Lecture organized in memory of the great scientist of our soil. I am sure most of you would be familiar with the name Dr. Thanu Padmanabhan, the great Indian physicist who left us on 17 September 2021 at an early age of 64. Born in Thiruvananthapuram, Padma Shri Thanu Padmanabhan's research was on the fields of gravitation and cosmology. This memorial lecture is a tribute to this great scientist who has contributed immensely to the cause of science, especially in the field of cosmology. With this brief introduction, let me move on to my duty of introducing the speaker. We have with us today Dr. P. Sreekumar, Satish Dhawan Professor at ISRO Headquarters, Bangalore, to deliver the first Dr. Thanu Padmanabhan Memorial Lecture. Dr. Sreekumar was earlier the Director of Indian Institute of Astrophysics, Bangalore. An alumni of IIT Mumbai, Dr. Sreekumar took his PhD in physics from University of New Hampshire, USA. Starting from his assignment as research scientist at NASA for about 10 years and then moving to India, Dr. Sreekumar has held several key positions in space research. He was a principal investigator for class payload on Chandrayaan-2. He is a recipient of several awards. Notable among them are the Chandrayaan-1 Payload Team Award in 2009 and the International Academy of Astronauts laurels for team achievement on Chandrayaan-1 in 2013. As of today, he has 19,899 Google Scholar citations and an H-index of 60. I'm sure he's the right person to deliver the first Dr. Thanu Padmanabhan Memorial Lecture as part of the 34th Kerala Science Congress. Sir, with great respect, on behalf of KSCST, I welcome you to this session for presenting this lecture. I understand that the beloved wife of Dr. Thanu Padmanabhan, Mrs. Vasanthi Padmanabhan, has joined this memorial lecture session. Ma'am, we are blessed to have your presence here. On behalf of KSCST, it's my pleasure to welcome you to this session. Also, extend a hearty welcome to all dignitaries, delegates, scientists, students, and my colleagues to this session. I now request Dr. Sreekumar to present the lecture. Over to you, sir.
Thank you, Professor Lekha. And thanks to the Kerala State Council for Science and Technology and Environment in inviting me to present a talk in memory of Professor Thanu Padmanabhan. As you know, he is someone that the world knows very well as a theoretical physicist and cosmologist. His contributions in areas of gravitation, structure formation, etc. are very well known. He was an excellent teacher and a communicator of science, which is a very important thing and a very rare quality in often in front-ranking scientists globally, and an exceptional science writer, both in research and in popular science. Of the many recognitions received, the KSCST's Kerala Shastra Puraskaram in 2021 is certainly one of the more prestigious ones that he has received. This morning, Professor Ramachandran spoke about the importance of inculcating scientific temper in the country. Way back in the 70s, while I was in high school, I used to stop by the Trivandrum Science Society, which used to run classes in the PMG Junction. And these classes were taught by a few key members of the Science Society. And one, Dr. Parameshwar Nair, who is currently in the US, and Padmanabhan was part of that. And they would teach us very interesting advanced topics in physics. And my introduction to Lagrangian was really coming from these lectures. Though I probably did not fully understand it at that time, it certainly had a certain charm to it. And I'm sure it has given me that impetus to really pursue physics as a career. And I'll always be grateful to Professor Padmanabhan and his team for that wonderful opportunity. Professor Padmanabhan was not an experimentalist. However, he was deeply interested in experiments and experimental results. And in recent times, he's interested in encouraging large astronomy projects in the country necessary to really do the kind of global science that we are all desire, that we like to do. His interest also extended to the area of space arena as well. And we have talked much about it during my visits to IUCAA, or when he has, of course, also come for visits to Indian Institute of Astrophysics, and how we need to really do proper corrections and reforms to bring the system towards greater efficiency and impact on society. So today I've chosen to speak about two space missions, and one that's completed and one that's coming up. And I'm sure this would have been of great interest to Professor Padmanabhan professionally. And with the theme of the Kerala Science Congress on science, technology, and innovation for transition to a knowledge economy, I hope to pursue this talk. This talk will shed some light on the technology innovation that are driven by fundamental science research experiments. So with that, let me just begin with a few introductory slides on our current approach to science. Our scientific thinking of the last few centuries showed that there's a quote from Brian Greene's book that patterns found in terrestrial and astronomical data made it increasingly clear that there is an order to the comings and goings of the cosmos, an order accessible to careful reasoning and mathematical analysis. The happenings in the universe are not only explicable, but predictable. So there is a formal foundation that we see in the way science has evolved. And in the last century, where Sir Isaac Newton laid the foundations of classical physics to describe motion, James Clerk Maxwell laid the foundation of electric and magnetic forces, Albert Einstein laid the foundation of relativity, modification of classical concepts of space and time, and certainly with the notion of space as not being absolute. And to the early 1900s, it was firmly believed that the past and the future are fully determined and tightly coupled to the present. There was no uncertainty about these things until the emergence of quantum mechanics, which showed that even the perfect measurements of today can still only provide probabilistic prediction of the future. Reality remains ambiguous until probed. These are, of course, very revolutionary thoughts that has evolved in the last century. In terms of astronomy, modern astronomy has emerged quite a bit in the last 100 years as well. Major revolutions have been seen. With the 1919 solar eclipse test, which tested Einstein's general theory of relativity and showed evidence for curvature of space-time near the sun, Hubble's discovery of the expansion of the universe was a very important discovery from the perspective of understanding what could be the nature of this large universe. The Big Bang evolution of the universe, discovery of matter that doesn't necessarily emit light, but exerts gravity, what we call as dark matter in galaxies. And of course, a background of radiation in the microwave and leading to deriving the age of the universe. And from an experimental perspective, the revolution that charge-coupled devices, CCDs, have made in both in astronomy and then subsequently in other applications that the common public has appreciated was a major contribution to astronomy. And of course, 25 years ago, the early discoveries of planets outside our solar system, which is a topic of increasing interest today. But now let me take a step backwards and ask a question that many would like to know, and that is simple question. How do you measure the temperature of a star? We go back to the concept of a black body that has been taught to us in schools. And it says it's a body that's in thermal equilibrium, it absorbs incident radiation, emits a characteristic spectrum, a distribution of energy as a function of wavelength, or what we call as a black body radiation spectrum. This is the shape of that spectrum, where what you have is along the x-axis, the wavelength plotted in nanometers and the power at each of those wavelengths. And what you see is a spectrum, a shape. If you look at the, I'm not sure whether you can see my cursor. Okay, and I hope you can see the cursor. What you see is a spectrum that shows a maximum at some particular wavelength and then falling off as the wavelength increases. This was, of course, formulated precisely by the Planck law. And what we see, for example, for a black body at 6,000 degrees Kelvin, the peak of the emission comes at close to visible. And then as the temperature goes to smaller values of 5,000 degrees Kelvin, the peak of the radiation spectrum shifts to lower wavelengths. At 4,000 degrees, it goes into the infrared part of the spectrum. So there is a connection between temperature and the peak wavelength of the emitted radiation. So this is a hint of how we can actually measure temperature of a star. We look at the star, the light from the star goes through a dispersive medium, and the most common one that we are aware of is a prism. And in the prism, it actually splits that into various wavelengths. And in a more sophisticated instrument, like maybe the Hubble Space Telescope, we would have what are called gratings that will actually tell you what is it spreads the light into finer wavelength band, or what we call as fine resolution. And it allows you to again ask how bright is the object at different wavelengths. So the approach would be to measure the intensity of light at different wavelengths, plot it as a function of wavelength, and check if the spectrum looks like a black body. If so, determine the peak value of the black body, what is the wavelength at which maximum emission comes out. And then using the theoretically derived relationship between wavelength and the peak temperature, determine the temperature of the object. So this is just what the relationship tells is the product of temperature and the maximum wavelength at which the emission comes out, the wavelength at which the maximum emission comes out, that product is a constant. So when T increases, lambda max decreases. So that's what I would see if I plot temperature versus peak wavelength. This is what I would see. And with increasing peak wavelength, the temperature comes down. If I were to do that, like in a real experiment, assume I have a spectrograph and I go out and measure for various wavelengths. I measure the energy density or the intensity. And then what I will then get is a set of points. As in any experiment, you then need to ask, does it fit the model that was theoretically predicted? And that prediction is what I'm trying to show with the green curve. Once I fit that best fit function, I can then derive what is the max wavelength at which you have maximum emission, which I call as lambda max. And with that lambda max, I move on to the other graph and say, here is lambda max, and what is the temperature for that lambda max, and I derive my temperature. So you're able to derive the temperature by measuring the spectrum of radiation coming from the cosmic object. So it's a very common thing that we do that it can extend to various wavelengths. Of course, at other wavelengths, the temperature, the process behind the emission need not be purely thermal. It could have non-thermal processes, but once we know what the model is, then we can use similar techniques to derive properties of cosmic systems. I want to now go to the larger problem of the universe and ask, can I derive a temperature of the universe in a similar manner? And what I do, if you look back in time, on x-axis is the time since Big Bang. So this colored area of quantum gravity is way back in the early days, for which I know nothing about, and very proficient scientists are still working on the concepts of quantum gravity. Professor Padmanabhan had certainly contributed to many of these areas. There is an area of inflation a little later, when the universe expanded by an enormous amount. And then, of course, subsequently, things started cooling, the quarks confined, the individual charged particles then combined to form neutral entities, atoms, which allowed light to stream out. Then finally, we have today, when we have structure in the universe, galaxies, stars, and various forms. And if I were to ask what is temperature doing as of over this time, what we see is a temperature which should have cooled, hot body cooled, And the question that naturally comes up is, the universe has been cooling. What is its temperature now? Can we measure that? And so just as a quick recap, the Big Bang universe says it was very hot and dense in the very beginning. It's been expanding. That expansion has been demonstrated through Hubble's observations of galaxies. And so he's able to relate the velocity of moving objects, which is derived from Doppler shifts. And we can connect that to distance to a constant that we call as Hubble constant. So photons interact with the electrons, prevented the light from escaping until about 380,000 years ago. And then all these escaping photons, part of it will also produce a background, and then neutral, the neutral matter that's left in started creating structures, and we see all the structures that we see today have evolved from there. So if you ask the question, has there been evidence for this? And way back in 1965, 1st July, Astrophysical Journal, there was a paper that came out that said a measurement of excess antenna temperature at about 4 gigahertz. And this was a paper by Penzias and Wilson. They found this excess antenna noise. And it's often said that this is the most understated title of a scientific paper, which has gone on to produce an incredibly important finding. The only reference to that is about this paper of Dickey, Peebles, Rolls, and Wilkinson, which was in the same issue of the journal, which gave a possible explanation for this. And that they connected to the early universe. And so this is a picture of the horn antenna that they used in a place near New Jersey, to really make this measurement. And that was reported in the New York Times, and in the Indian Express, this picture came where Penzias and Wilson measured a temperature of 3 to 3.5 degrees Kelvin for this temperature of the universe, and they won the Nobel Prize for that as well. So this is, I think, the current historic site that has been prepared. What's important here is also that in 1953, almost 12 years prior to this measurement, George Gamow, the Russian physicist, had actually predicted a temperature of about 7 degrees Kelvin, not far from what was actually been measured. So there's a theory, experimental discoveries, and that's actually a beautiful demonstration of how we can actually connect these two programs. Now, let me fast forward to 1989, when we have emergence of cosmology as more of an exact science with the launch of a satellite called the Cosmic Microwave Background Explorer, COBE mission, with the purpose to really study this background radiation that has been discovered by Penzias and Wilson. When you do a space experiment, we need to worry about many things, right? And we typically do experiments in space only if it cannot be done from ground because of cost of the mission, complexity, long development timescales, a lot of people involved, etc. And experiments are kind of extreme environments of space. But then there are advantages to set a radiation that will not penetrate to the atmosphere of Earth. And we have to go outside to do it. And so the microwave experiment, COBE, was also done in a similar manner. And what we then see is that within this COBE experiment, COBE satellite, there were 3 experiments. And today we'll only discuss one of them, which is a FIRIS experiment, which is the far infrared absolute spectrophotometer, which is a cooled interferometer with a goal to detect deviation from black body. So in 1965, when they saw the first evidence of the radiation, and theoretical arguments have actually already said this could be representing a black body spectrum, naturally scientists were very keen to ask, is that a pure black body or are there deviations from it? And those deviations would be of great interest to physicists. To precisely measure the spectrum in the 0.1 to 10 millimeter range, so that covers the range that we're now discussing. To do that, we have to have very precise temperature control and a lot of internal calibrators to make sure the experiment is done very precisely. So one of the points I want to emphasize in this talk is to say how precision calibration of experiments are critical to really doing absolutely front-ranking science. And this was an experiment that clearly demonstrated excellent things, and it ensured that it remained, the results had a large immunity from errors that are creeping systematically. So they used differential measurements to really ensure that the measurement accuracy is very high. And what was special about it, in order to do this very precisely, they had to even tailor the spacecraft separately, carefully. It had a rotation, about 1 rotation per minute, to really ensure large coverage of the sky. Then the angle, the view angle of the telescope was pointed not in the direction of the velocity vector, but offset pointed to ensure that the residual gas that is there even at these altitudes are not deposited on the optics and degrade the optics. They had special momentum wheels. Momentum wheels are often used to move spacecrafts in various directions, but to compensate for the angular momentum, they had another set of momentum wheels to create a net zero angle momentum system to ensure no disturbance is there on the platform. It was put in an orbit that is often called a sun-synchronous orbit. The sun-synchronous because the orbit of this spacecraft is actually normal to the sun always. So, which since the Earth moves around the sun in 365 days, roughly every day it shifts by 1 degree. The orbit also tilts by 1 degree, such that always the orbit of the sun, orbit of the satellite is perpendicular to the sun satellite vector. And so that way, thermally, it will have a very stable thermal environment. And then, of course, it had sun shields to protect against direct solar, because that also can actually produce perturbations that would be of concern. So a lot of effort went into making sure that the COBE spacecraft were actually designed very, very carefully. Now, just before the launch, we also noticed that there were interesting experiments that have been carried out in the interim. And in particular, there was a Japanese-American experiment that showed that the background radiation was not truly a black body. There were some deviations of excess brightness at some of the wavelengths. So this really had a very powerful effect on a lot of the astronomers working in this area. They were great excited to know what COBE has found. I happened to be in a lab that is next door to this building where the COBE work was going on FIRUS, and there were many times we had tried to find out what is the result. They would not reveal it, and we had to drive down to Washington D.C. at an American Astronomical Society meeting, where in a room some 300 people packed into a room to listen to the results from the COBE mission. And as often as said, this picture is truly worth 1,000 words. Because, these were the days when you didn't have projectors of the type that we now, PowerPoint projection was not the standard, but view graphs were used. And the scientist in charge slowly pulls the sheet off the view graph, and you started seeing the spectrum. And this is a spectrum that was shown. What you see here in red dots are the actual measurements, and in blue is a theoretical blackbody spectrum, and it's a perfect fit. The fit is so good that you won't be able to see the error bars. And in order to see that, you have to exaggerate the error bars. And here is a plot where the error bars have been exaggerated by 400 times for you to see. So you can imagine the precision which this measurement has been carried out. And that gave rise to a number of 2.725 plus minus 0.002 Kelvin as a temperature of the cooling universe. Quite an impressive result, I would say. And it remains today and so this is a major breakthrough of the COBE team. And so the Nobel Prize in Physics was awarded to John Mather, who is on the left side, and George Smoot, who worked on a second experiment on COBE for their discovery of the blackbody form and anisotropy, the cosmic microwave background radiation. By the way, John Mather on the left is also the key scientist in charge of the James Webb Telescope. And it tells you the precision which he's actually, as an experimentalist, what a high quality of experimentation he was bringing to the team. I now move to the second mission that I want to discuss about, and the topic is on gravitational waves. The existence of gravitational waves have been propounded by Albert Einstein in 1915. Just as we know, accelerating charges produce electromagnetic waves, accelerating masses should produce gravitational waves. And that is understood because we do believe that when big masses move, it is like causing ripples in the space-time. And that is what we set out to do. And there were a lot of experiments trying to look for gravitational waves. And as part of this effort to look for gravitational waves, scientists have been looking at binary systems, for example, where you have two compact stars, often neutron stars, which have a tight binary, and you can measure their periods, their distance separating them, etc., very precisely. And a particular system called PSR, which is pulsar B1915 plus 16, these coordinates, these are represented the coordinates in the sky. They showed signs of losing energy, and that is derived from the pulsar parameters of the fact that distance separating them was actually coming down. And they observed that, and they found that the loss of energy from this pulsar system, the binary system, is exactly equal to what you'd expect from relativistic, general relativistic prediction arising from loss of energy into gravitational waves. So this was a very clear indication of the fact that gravitational waves exist, and moving masses can indeed produce them. Now, and they, of course, that pair also won the Nobel Prize in 1993. Now, if you were to now go a bit further and ask, instead of just in spiraling about a common center of mass, if we were to really then push it to the end where it actually goes to a merger, then you would expect to see a wave which has a pattern that would show increasing frequency very rapidly, and that was predicted theoretically. And so to measure that thing, you would actually measure distances between objects as the gravitational wave passes through them, and these distances would change by a tiny amount. And this relative change in the distance between masses is often used, we use a term called strain. And the gravitational wave laboratories on Earth, called Ligo, Laser Interferometer Gravitational Observatories, 2 of them, they had to measure a strain where the change in length over the length is of the order of 10 to the minus 21. It's an extremely challenging task to undertake. So there are these 2 LIGO labs, one in Hanford and in Washington State of the United States, the Northwest, and then a second one in Livingston in Louisiana, near Louisiana, about 3,000 kilometers away. And each of them have 2 arms. Each arm is about 4 kilometers long, and they act like a Michelson interferometer where you look for small changes in the path length from suspended mirrors, and that would be indicative of the detection of gravitational waves. And in September 14, 2015, nearly 100 years after its prediction, the first of these signals were seen between 2 black holes when they merged. And this is the theoretical spectrum that was expected, what is often called a chirp signal. And the chirp signal was also seen experimentally both at Hanford and at Livingston. This is the pattern that you see in the 2 plots. So, and this now tells us a lot about the two black holes involved, can get a measure of their spin, distances, masses, many things. This is an important discovery, and there's been subsequently many more discoveries from the LIGO collaboration, as well as the European Virgo collaboration, and soon to be a collaboration coming up from Japan. We also have a program in India. A LIGO lab is being set up in India, in Maharashtra. LIGO India is coming up in about 6 years. And that should, in turn, help reduce the error boxes with regard to its positioning on the sky. Remember, these individual LIGO laboratories cannot tell you where it's coming from, but when you're using relative timing, they can actually narrow down to certain parts of the sky. But narrowing it into a smaller error box is very critical if you want to really follow that up with other telescopes which have very narrow fields of view. Now, these were all Earth-based laboratory, and it has some limitations. If you look at this plot on the right side, where I have put in this colored rectangle, that shows roughly the zone where LIGO, Virgo, and the Kagra, the Japanese Kagra instruments, are working. And what you see in this yellow, in this green curve is very quickly, as you go to lower frequencies, you see increasing seismic noise from the ground itself. And there is no escaping that here on. So the idea that was proposed in an experiment called LISA is to go into space and actually so that you can escape the seismic noise and then look at those frequency domains which are involving ultra compact binaries, extreme mass ratios of binaries, etc., that are critical to other kinds of science we can do with gravitational waves. So with that in mind, the second experiment I want to discuss is the Laser Interferometer Space Antenna, or called LISA. This was, I think, initiated around 1995. I recall discussions in the corridors of those labs where they talk about this, and it's now scheduled to be launched in 2034, nearly 40 years of effort. So how does LISA detect gravitational waves? It actually gravitational waves create time-varying stretching of space-time, which appears as a change in distance between two objects. So if you have two objects suspended in space, undisturbed in any manner, their distance between them should be the same, should remain unchanged until a gravitation wave goes by, and you see small changes in that distance. If you can measure that, that's a way to measure the gravitation wave. So the distance between two test particles freely, okay. So it measures these small changes. So here's a cartoon that I've just tried to draw to indicate it. Yes, it'll say spacecraft 1 and spacecraft 2, separated by a distance d2, and within each spacecraft there is a test mass that is at a fixed distance d1 from the edge of the spacecraft, d3 for the spacecraft 2, and you measure. If you are able to maintain d1 and d2 very precisely, then any change in d2 would be an indication of a gravitational wave incident on the system. So to address this, you have to have 3 spacecrafts freely flying in space that will oscillate together and look for this wave as it goes by. It's basically looking for ripples at the level of few minutes to a few hours. And the change in distance, one can imagine, is very tiny, few part in 10 to the 21 or 10 to the 22. A typical separation we're discussing is, I think the LISA project began at 5 million kilometers, then went back to 1 million kilometers. Now it's 2.5 million kilometers. And so that will talk about separation at the level of 2 to 3 picometer separation is what we have to measure. Over a short intervals of time, of course, over long intervals of time, this number might change. Absolute challenge, and the way they do that is by putting these 3 spacecrafts in an equilateral triangle configuration in the same orbit as Earth, but following Earth, a little behind us as we go around the sun. So that's the plan. And it, of course, has enormous challenges because you have to make sure the system is free from any disturbances. So the payload has to control the position of the spacecraft. The spacecraft actually becomes part of the payload, part of the experiment. So you have to move the spacecraft around this test mass such that the distance between the test mass and the edge of the spacecraft is maintained at all times, which is why sometimes they have been calling this a science craft, not even a spacecraft anymore. We often do the standard structural and thermal analysis to really make sure everything survives, but now you have to also worry about gravitational effects at very, very fine levels. And there are noise in the spacecraft that arise from firing of thrusters, solar radiation pressure, which is another major factor that actually can influence this, because it's not constant, as small changes in the location as well as in the reflective surfaces of a spacecraft can actually change the pressure from solar radiation. And since it was a very, very challenging experiment, the LISA collaboration created a sort of a prototype mission called the LISA Pathfinder. And that flew where it had 2 test masses in a spacecraft, and it managed to move the spacecraft around these test masses such that the distance between the test mass and the spacecraft remained constant. What is shown on the right-hand side is a plot where the hatched part is actually the area that was required by LISA. But the Pathfinder mission actually, if you see in red, it actually performed better than what was required by the LISA requirements. And that has been an incredibly major achievement because it reduced tremendous amount of risk that was associated with this mission and demonstrates picometer laser metrology can actually be done. So now it makes it viable for the LISA Pathfinder LISA mission to actually take off. And in all these experiments, as in the previous one, we find that when you want to do this, you have to control systematic noise in the system. All laser sources fluctuate. And one way to do that is to do comparative things that actually allows you to use, make the result insensitive to those fluctuations. And the concept of an interferometer using such systems is what has actually been implemented in LISA. And so we see interferometric techniques, which was also used in the very 100 years ago to really look at, was light traveling through a medium called ether. And that was also the famous Michelson-Morley experiment, also used an interferometer. Interferometry is a very powerful technique to really do high precision experiments. So what have we learned in this process? Space experiments are enormously challenging. It demands high level of design, reliability. Once the experiment is sent out, we have no access to it, so everything has to be done with careful planning, prototyping if required, such that your goals can actually be met. You have to understand the instrument thoroughly. Systematic errors are a real problem. Ability to really translate measurements to science really depends on how well you understand the instrument. And that's a very, very critical issue. And you have to calibrate it. So the calibration is a process where you give a known stimulus to the experiment and ask, what is the response? And make sure you fully understand it for the range of stimulus that you expect to see. And you cannot always exactly emulate the expected universal signal, but there are ways to really at least address it in simulated in some fashion. So this is a very critical part of any experiment. So we saw the COBE experiment, which was done with such care, yielded excellent results using the strategy, where they used differential measurements and had onboard black bodies that are very carefully controlled that acted as stable references against which we actually made these measurements. So that's how we were able to measure that black body curve to such extreme precision. We also discussed a future mission that promises exciting results. That is the LISA mission. And the Pathfinder showed excellent performance. They reduced risk by actually having a trial mission ahead of that. So theory and experiments march hand in hand. One drives the other to really do it. Sometimes new experimental capability allows us to address new theoretical predictions. And so they march hand in hand. Good design, good calibration, prototyping are all absolutely key to success. So in closing, I just want to say that Professor Padmanabhan, with his deep interest in cosmology and fundamental processes, I've been absolutely thrilled, I'm sure, in the early 90s when he heard of the COBE results on the cosmic background spectrum. The COBE, of course, had two other experiments, as I mentioned, and that actually led to more interesting stuff regarding fluctuations and structure formation, on which he has actually contributed much. If he had not left us so soon, he would certainly have been thrilled to see the results from the LISA mission, expected now in the mid-2030s. There have been some initiatives in India also on similar programs. For example, there is an experiment called CMB Bharat, spearheaded by Professor Tarun Savradeep, who's now the director of the Raman Research Institute. Before that, he was at IIAP, which actually attempts to redo FIRUS, the COBE black body spectrum measurements, using a more sophisticated version to really improve the quality of that measurement. Lots of challenges, so it's a very early phase. There is also a very tiny group that is just debating quietly in the background about the possible role for a space-based gravitation wave measurement. Now, LISA, of course, is there at those millihertz regime, but there's a gap between which covered by LISA and the region covered by ground-based LIGO observatories, and that is from about 10 hertz to about 0.1 hertz. And that's a very interesting area for study, and there is a small group trying to see, can we really contribute to that, maybe probably through an international collaboration. So these programs show that the deep involvement of students in such projects are key. Many of them involve large number of students. In India, for many reasons, we are not able to have large number of students involved in such long-term programs. Some of them, they say it's because it'll take too long for them to do their PhDs, etc. But there are ways to address it. And but involvement of students in such programs are very key to developing advanced skill development and to push our own research frontiers. And the discussion, the topic of knowledge economy, on which this conference has been discussing quite a bit. So I truly hope that is something we will be able to address better in future. And I hope some of you listening into this will really take up this challenge and will really make us happy in future if you're all part of such programs. Let me stop there and answer any questions. Thank you.
Thank you, sir. Thank you for the really interesting and inspiring lecture. Now the platform is open for questions. Participants can post their questions in the chat box. In the meantime, sir, I just would like to ask more about the Ligo India project. So what are the main or major objectives of this project? And what was, is there any specific reason we are setting up a Ligo at a particular space or a particular area?
Oh, particular, why India and...
Yes.
Okay. Because the reason, as I mentioned, there are 2 LIGO labs that are now operating. From 2015 onwards, they've been seeing these events. And These events, as I mentioned, doesn't tell you exactly where it's coming from, which is very important information we need to gather, because we like to understand what is the conditions under which such things are produced and so on. And to do that, you will need to really have smaller or finer localization from the events. Right? Gravitational waves have to be localized to better, to smaller error bars. To do that, you will really need a third LIGO labs. And so the LIGO, after much study, came to the conclusion that it is something we can actually do if it is positioned in India. And that's the prime objective of actually having an experiment in India, to really reduce error bars, such that a follow-up can be done by large telescopes, which typically have less than a degree field of view. And you need an optical telescope to look at that zone to really quickly capture this. So that's the real reason. So hence the localization, reason for it to be in India. And that is what we hope to achieve in the next few years. Yeah.
Okay. And I think IIAP was really involved in that project. And I think Professor Thanu Padmanabhan was also involved in that project.
Yes. IIAP is a lead center along with the Plasma Research Institute and the RRCAT, the Department of Atomic Energy mission at, the institute in Indore. These are the three key players. And there are many other people around the country involved in that issue. Yeah. Very, very challenging experiment to pursue. Yeah.
Yeah. Thank you, sir. I think we don't have any other questions from the speakers, from the participants. So let me invite Dr. E.S. Anil Kumar, scientist, Kerala State Council for Science, Technology and Environment, to propose the vote.
Am I audible?
Yes.
Yes.
Respected distinguished speaker, Dr. Sreekumar sir, other dignitaries, dear colleagues and friends. We have listened a highly informative talk delivered by Dr. P. Sreekumar, the former director of Indian Institute of Astrophysics, in connection with Dr. Thanu Padmanabhan Memorial Lecture. On behalf of the organizing committee of 34th Kerala Science Congress, I extend my sincere thanks to you, sir. I extend sincere thanks to Dr. Vasanthi Padmanabhan, wife of late Professor Thanu Padmanabhan, for attending the memorial lecture. I also thank all participants. Thank you all.
Thank you, sir. Thank you, Sreekumar sir, for joining us today. It was really interesting to listen to your lecture. And thank you all participants. We will have the second memorial lecture, Dr. P.K. Gopalakrishnan Memorial Lecture, immediately. Please stay connected. Thank you.
Shall we start, Arjun?
So 1 minute, let me check about the details of speakers.
Dr. K. Harilal, I think he's joined now.
Yes, I'm here. I joined.
Harilal, sir?
Yeah, Arjun.
Yes, yeah.
Harilal sir joined.
Yeah.
Okay.
We should start, right?
Sure. So,
Yeah.
welcome
Good
to
afternoon,
our second memorial lecture.
everyone. Yeah. Yeah, let me start, Arjun. Okay.
Sure, sir. Thank you.
Thank you, Arjun. Good afternoon, everyone, and welcome to Dr. P.K. Gopalakrishnan Memorial Lecture of the 34th Kerala Science Congress, which will be delivered by Dr. K. Harilal today. Before I introduce Dr. Harilal, let me talk a few words about Dr. P.K. Gopalakrishnan. Dr. P.K. Gopalakrishnan is an eminent sociologist and economist who played a crucial role in formulating the science and technology policy of Kerala in 1972 and in establishing the R&D institutes under it. He took his master's degree from the Institute of Social Sciences, The Hague. He completed his PhD in economics, social sciences from Amsterdam University. Professor Timbergergen. Dr. Gopalakrishnan, who was originally called PKG, had occupied many important positions in the government of Kerala. He was associated with different capacities with the Cardamom Wage Board, Taxation, Equity Committee, Labor and Industrial Special Secretary to Planning and Economic Affairs Department during 1974 to 80. This year's P.K. Gopalakrishnan Memorial Talk is delivered by Dr. K. Harilal. Dr. K. Harilal to his PhD in economics from Center of International Relations, Mahatma University as a faculty member, and later joined in the Center of Development. He has about 24 years of teaching in the area of international political economy and regional economy. Trade policy. Professor Harilal was a member of Planning Board during 2016 to 2021. He has now in development practice through his activities as a member of Planning Board, member of UNIDO, member of Group of Land Reforms, member of Steering Committee for 95-year Plan, Government of Kerala, etc. He's in understanding the development in the world trading system at multilateral and regional levels to see how regional developments affected the state's economy. Once again, I welcome all the friends, especially Dr. P.J. Lada, who is the former director of TPGRA, who is also the daughter of Dr. P.K. Gopalakrishnan. With these few words, I invite Dr. Harilal to deliver the memorial lecture. Over to you, Dr. Harilal. Sir.
Dr. Arvind, Dr.
Yeah.
And other friends. Good afternoon, everybody. I consider this as a great privilege to have got this invitation to deliver P.K. Gopalakrishnan lecture. And the topic of my lecture, knowledge economy and development planning, is an area where P.K. Gopalakrishnan is remembered for his brilliant contributions. No doubt, Dr. P.K. Gopalakrishnan was a great visionary. But in my opinion, he was more brilliant in implementation, in praxis. He converted great ideas under the leadership and guidance of Chief Minister C. Achuthamenon and others into practical policies, implementable projects, and great institutions. And some of these institutions are key institutions of Kerala's knowledge economy. And they have contributed immensely to the development of Kerala. And I can state this with full conviction because I represent Center for Development Studies. I studied there. I'm teaching there even now. So I have long years of experience in one of his institutions. And I also followed him as a member of the Kerala State Planning Board. Now, I shall have occasion to speak about his contributions later in this lecture. Before getting into that, let me broadly define the contours of my presentation today. Since I'm giving the P.K. Gopalakrishnan lecture, I think it is logical to define knowledge economy from the point of view of praxis, from the practical point of view. What do we mean by knowledge economy? From the point of view of everyday life, I think knowledge economy should help us harness knowledge to improve our life in all its spheres. The knowledge content of all activities, everyday life activities of the people should improve. And if we take such a definition, it will be an inclusive definition. It will be able to include everybody in the society in that definition. Now, why should we try to improve knowledge content of all activities of life? What should be the goal? Now, if this question was asked a decade ago, my answer would have been very clear. It should be to improve production, productivity, and growth. But this growth and production oriented view is slowly fading because people are realizing the importance of other dimensions of life. It's very important to ensure social justice. Growth is important, but environmental sustainability cannot be compromised. Social justice cannot be compromised. And harmony should be cultivated. Peace should be cultivated. Happiness and well-being are very important. So we cannot exclusively focus on production and productivity and growth. There are so many other virtues that our societies wish to pursue, wish to nurture. All those virtues that societies, communities wish to nurture, that should be taken care of by the knowledge economy, by the use of knowledge. It need not be always focused on increasing production. Suppose we are increasing production of agricultural products. We may have a very high growth, but if it is not benefiting farmers, if it is not benefiting agricultural laborers, and if it is ruining environment, what is the point in having high agricultural growth? So we are increasingly aware of these dimensions of life, values, and therefore knowledge economy should be aiming for achieving these other dimensions as well. Now, in the context of Kerala, when we define the goals of knowledge economy, we cannot take a autarkic view of things. We cannot be very inward oriented because we are in an interdependent world, and Kerala, for that matter, was a highly globalized society even earlier. We import a lot and we export a lot. We need to export. We need to export to the world markets, less of the nation's market. So we need to be very competitive. And in fact, it is not just a question of exporting and being competitive in the international markets. In fact, now because of the globalized economy, our borders are porous. And therefore, if you want to sell in the Chale market, in the domestic market in Kerala, we need to be very competitive because now we will have to compete with other states and other countries to be able to sell in our market. Not only goods, but services and other things. So we should be able to export goods and services, technology, know-how, knowledge, labor power. These are all important. And for pursuing those objectives, we should be able to use knowledge and knowledge economy institutions. Now, how are we going to pursue the objective of furthering or strengthening knowledge economy institutions? Here again, the answer is very simple, known to all of us. If you want to have the knowledge economy thriving in our society, you need to really make huge investment in universities, higher education institutions, science and technology institutions, research institutions. And we should also develop structures, legal and social, cultural institutions so that innovation is promoted, invention is promoted, diffusion is promoted, and research is promoted. So we need to invest in these things so that the innovation system is strengthened. The right kind of ecosystem is promoted for knowledge generation and diffusion. This is the typical answer. And there are broad agreements on this, no doubt about it. But again, in the context of P.K. Gopalakrishnan lecture, I think I should take a practical view. And my experience in the planning board also prompts me to take a practical view. Instead of straight away quoting theories or explaining theories, let me start from a everyday kind of situation. Let us imagine that we are going to the district PWD office. We meet the engineers there. We ask them about the state of roads in the district. The engineer or the group of engineers there will be able to explain about major roads in the district, the state of those roads, and they'll focus mainly on the work in progress, where the work is getting completed, which are the works which are getting delayed. All those things they will explain. The focus will be mainly on the current projects in progress. And it's very unlikely that they will be explaining to you the road map of the district, connectivity map of the district, how it looked like, 30 years ago, 20 years ago, 10 years ago, and how it is now, and how they think it will emerge and evolve after 10 years or 20 years. And of course, other transport systems, demography, urbanization, urban planning, the way economy is developing and how the road system should respond. These things are very unlikely to come from the PWD engineer. Of course, they are all doing good work, but this kind of knowing what they are actually doing, that may not be forthcoming from a land department office. I'm just mentioning the PWD office, but you go to the water authority office, you go to the irrigation office, you go to the district medical officer's office. Everywhere, in most places, this will be the situation. This is not only of the government offices, other offices also you'll feel the same issue. In the sense, we may not be knowing about what we really do, from full implications of what we do. When we think about new knowledge, we should also think about the current knowledge. What is the kind of knowledge that we are applying about road technology, road building technology, but the larger context of area planning, spatial planning, development planning, in which building a road should be done. In the area of medicine, we focus mainly on cure, on treatment, and we don't get into research much. In fact, our doctors are aware of this limitation. Our medical colleges, except for Srijitra and some other institutions, most of them focus on treatment, which they are doing very well. We all are beneficiaries of that. We learn from companies, other institutions, and we implement those things here. But the state of affairs as far as knowledge is concerned, we are not trying to reach horizons. We are not trying to reach frontiers in many of these areas, and we are also not properly aware of what we are doing or the current state of knowledge in many areas. Now, if we are not having this, if you don't have a proper idea about the way water resources are being managed in the state, we cannot easily think about future techniques of water management. And this is what happened to our universities. Our universities in India, including India, they were blissfully unaware of problems of life around. What is happening to irrigation in Kerala? What is happening to drinking water shortage in Kerala? What is happening to our animal husbandry, crop husbandry? That kind of existing state of knowledge, we were not properly aware at the university level. This disconnect was there. They were giving degrees, producing degrees, and teaching and learning. But and also they were keeping up with knowledge everywhere else, but not so much about the local life. These institutions were not embedded in local life. That is where this C.H. Menon, P.K. Gopalakrishnan and others decided to start some of our leading science and technology institutions like CES, TBGRI, CWRDM, and many other institutions. I'm not mentioning those names. CDS is one of those institutions. These institutions were meant to be locally embedded, and they in fact tried to do so, and they made a mark. They made a major difference in Kerala. Like CDS started studying about local land relations, agrarian relations here, about demographic profile, changes in demography, about migration, about different aspects of life of people of Kerala in different contexts. Similarly, CES started studying about geography and geology of Kerala, problems related to that. They started interacting with local people. They started interacting with political parties. They got into debates. They helped the environment movement. And that made a major difference in the quality of democracy here, in the process of generation of knowledge and technology here in Kerala. And that was slightly different from the experience of universities. I think this is very important in thinking about knowledge economy in the future. So it's very important to know about the current state of knowledge, how we are doing things now, our everyday life activities, how we are doing those things now, what is the core knowledge content now. That understanding is very important to think of future. Think of new technologies to be taken, new knowledge to be brought in. And that is sadly missing in many areas. Like take the case of governance. Now, how much is the knowledge content, information content of our governance? I can tell you from the example of tax administration. How much we know about who is paying tax, which industry is paying tax, which entrepreneur, which trader is paying more. In fact, no, we are living in a highly digitized economy. We have information, and we have supercomputers, and many of the supercomputing jobs can be done now in a small computer. We are not really using knowledge. We are not really using information currently in doing things in our established way. So that's very important. Without really knowing about the ground situation, we cannot think of future technology, future knowledge. And that's the challenge. That's a major challenge that our planners and administrators who are having this responsibility of developing knowledge economy will be encountering. Now, let me also say that it's not going to be a simple, easy job, because now we are thinking in terms of large number of centers of excellence, investing, making huge investment in universities. Now we have a fiscal problem. We are having certain fiscal constraints. We can borrow, we can mobilize funds from other sources, but no, there are limits. Not only of finance, that's very important to underline here in this gathering. More than finance, you need personnel, you need people, you need time, you need attention. And many of these centers of excellence came up over a period of time because there were people ready to give leadership, invested so much time, intelligence in developing these institutions. So when we speak about centers of excellence, it's a big challenge. The government of Kerala is taking up a big challenge. If you want to establish a dozen centers of excellence, that's a feasible objective, but even that is challenging. But if you are extending that beyond a limit, it will be difficult. Let me give some experience of mine in government. See, over a long period of time, government of Kerala, we all know, it was not in a position to really invest in higher education institutions. We were not giving enough money to the universities. We were not giving enough money to the science and technology institutions. We know that. Not because the government wanted to neglect these institutions. Very often, certain other priority areas came up. And higher education institutions, science and technology institutions could not be looked after properly. And I can give you one very interesting instance which I used to really tell leaders and ministers and government secretaries to convince them. See, when I studied at Karyavattam, early 80s, Karyavattam departments had more faculty than, say, 25 years after that. Economics department where I studied, in between, now I think the situation is better. In between, there were only 2 or 3 people there, faculty members there. This was true of other departments at Karyavattam. And Karyavattam as a campus itself looked more vibrant in terms of number of people, presence of people, seminars, etc. So in early 80s than it was in the last decade. After that, of course, we have been able to fill vacancies. Faculty recruitment is taking place. Things are improving. But we lost valuable decades in between. And in other places, mainly because of central universities and all, higher education institutions were growing fast. So it's very important to continuously support these higher centers of knowledge creation, knowledge dissemination, universities and science and technology institutions. Here I should mention again, these are all practical issues. See, universities, when you allocate money to universities, I've noted, I never had this higher education as my portfolio in the planning board. But I have proper information about what was happening. I'm sure about what I'm saying. See, when you allocate money to universities, the first priority always goes to infrastructure building. Of course, salary and other things you cannot change. Development expenditure, development funds, mostly it is allocated for buildings. Because universities are having this works department and some engineers are there, they need to have work. And I can tell you that some universities in Kerala, there is not even some squares, space available for any more construction because it's fully populated by buildings. And vice chancellors and professors complain that we have too many buildings on the campus now. In CDS, we have decided that we will not construct any more buildings because we have too many buildings. So priorities also are important. Now, in a university higher education institution, faculty positions are very important. Faculty positions cannot stagnate. It should increase. You need to have good people also. In the recruitment, you should be fair, and number cannot be reduced. Similarly, library, laboratory facilities, you cannot compromise. So priority is certainly very important. And I have another very important point to make here. See, it is not that the Kerala government is not spending enough money in higher education. We are spending too much. in higher education, but lot of this money is going to aided colleges and of course, government colleges. We have large number of higher education institutions, senior colleges, and a substantial amount of money is going there. That is why universities cannot be given a lot of money. Science and technology institutions cannot be given money. Now, we cannot do away with all these colleges. They are doing a good job. But no, they can be improved from the current situation of teaching shops, factories producing degrees. From that kind of situation to embedded institutions, which can help people in everyday life for giving knowledge, which can improve knowledge content of activities of people. Say local governments, for example, they want to improve their animal husbandry sector, crop husbandry sector, drinking water, so many other problems they face. They need help, they need support in terms of technology, in terms of knowledge. Now, like the science and technology institutions started earlier, our colleges with so many faculties with high qualification, research experience, they can certainly play a different role. And in the knowledge economy that we are planning, I plead that the government should try to have a plan, very detailed plan, where the college faculty and the students there, they are involved in a big way. That is for mutual benefit, because knowledge can be produced, useful knowledge can be produced when you are locally embedded. You know about real life. You know about different dimensions of the way economy, society is really functioning. Say, for example, urban planning, spatial planning. We have Trivandrum, Thrissur, all these major cities. Now, these are theaters where you can experiment, you can study your urban planning or spatial planning techniques. You can experiment your transport planning techniques. And before that, you should know about Thrissur, how you should know about Trivandrum, about urban development there, problems related to urban development. Now, if you do that, then your knowledge, the process of making knowledge will be all the more simple and easy and meaningful if you do that. So the colleges should be encouraged to do this. Some departments in some colleges already are doing this. They are involving. They are making their local presence. Now, this is the only way. In fact, in many other countries, the universities certainly are working with industry, with farmers, with development departments, with welfare departments. So we should also develop this culture in higher education institutions. And I think these are the areas where the experience of P.K. Gopalakrishnan should be guiding us. And this is one thing that we should be able to learn from their experience. And I'll conclude by making one or two more points. How much time I have now? I don't know.
Probably can take up to 3:30. 5 minutes or 10 minutes you can take.
Okay. I would like to mention one more point, which is discussed in the context of knowledge economy here. In fact, now the discussion on knowledge economy here got this tempo because of the presentation of the last budget of Sri T.M. Thomas Isaac. That budget, in fact, announced some of these major objectives, and Kerala society sort of welcomed this, and a lot of discussions had taken place. And in that budget, emphasis was also given on export of manpower, on using digital platforms for preparing us for changes in the global workplace. We know that life is shifting more and more towards the virtual sphere. This is affecting every walk of life: retail, trade, manufacturing, culture. In every walk of life, you can see this shift. Work is shifted from offline brick and mortar centers to digital spaces. That is happening in a big way. And if you take the patterns of change in labor market all over the world, this shift is noted. So you are likely to get a lot of jobs in through the digital platforms, and you can work from home. You can work from your locality and work for global clients. That kind of a situation is coming up, and we should be preparing for this, because we are an out-migrating state. We have people everywhere in the world, and that migration patterns will continue, but the new opportunity is going to come. And in fact, the real migration trend may also get affected because of this online possibilities. So the budget made a bold move to invest in infrastructure facilities, so that now we can tap on this growing component of the global job market. And in the knowledge economy discussions, this is also very important. And our science and technology institutions, higher education institutions, should be on their own preparing for the change situation. I have a caveat to add. That's the only thing that I wish to mention here. See, in the international labor market, international job markets, it's very important where we enter, because a lot of cheap work is being generated. A process of cheapening of labor power is happening globally. And we know about gig workers and all. This is a very dangerous development in the labor market. We are experiencing this, and workers, their interests are not protected, and they are not even referred to as workers. They are treated as business partners. There is no room for collective bargaining. So many of these platforms can turn out to be highly exploitative. And it's also very important that therefore we develop knowledge so that we can compete in these platforms, participate in these platforms without being very badly exploited, without compromising on some of our bargaining power, without selling our labor power so cheaply. So this aspect is very, very important when we participate in the knowledge economy. When we participate in the knowledge economy, certainly it should be for our advantage, and that cannot be taken for granted. We simply swim into the world economy, knowledge economy in the world, and we will benefit. That's a wrong idea. It is too altruistic to have such assumptions. One needs to be very careful. One needs to make planned move, and in that also knowledge plays a very important role. How should we access these platforms? That should be guided by our knowledge about the platforms. That should be guided by our knowledge about these international job opportunities in the virtual sphere. So there again, our higher education institutions have a very important role to play. And higher education institutions, universities, and science and technology institutions will also have to bother about global workplace, how it is developing, how it is evolving, and how can we participate there. Our graduates, how can they go and participate in those spaces? We should consider this aspect also very seriously, and that's how we can honor and remember people like C.H. Menon and P.K. Gopalakrishnan. Thank you for this opportunity again.
Thank you, Professor Harilal. I hope we can take a couple of questions, right?
Yes, yes.
Yeah, there are few questions in the chat box. Can I read out for you?
Yeah, please read out that because others can also.
Yeah, there is one question from Arjun Prasad from KCST. The question is, will developing researcher, policymaker, practitioner models helps in better policy making and effective implementation of projects scientifically?
Sure, there is no doubt about this, and this is missing in a bad way in Kerala. Of course, there are some areas where such dialogues and cooperation take place, but in many areas this is not happening. I don't have any hesitation in saying that the bureaucracy is very hesitant in promoting this. The bureaucracy is very hesitant in promoting this. They may pretend that their ideas are welcome, knowledge is welcome. In fact, when it comes to real practice, their ego will be hurt very badly.
Right. Yeah.
Their ego will be very hurt very badly when some scientists explain, and give knowledge. These are the possibilities. This is a problem. In fact, that should be. And I mean, the bureaucracy at various levels and top bureaucracy particularly, it's an unfortunate thing, and we should change that situation. The bureaucracy department should be more receptive, and of course, the other side is also true. In universities and higher centers of knowledge, they are very keen to publish in peer-reviewed journals, scoring their points and marks and looking for promotion or their recognition among peers. That's what bothers them, and they don't care about what's happening to our industry, our production. Sometimes the bureaucracy is hostile, government is hostile, not very keen to listen to. So they think, okay, happy, let them have their fun, and I'm having my fun. Yeah, thank you.
Yeah, thank you, Professor. And there is one more question. Can you explain the importance of private firms in knowledge economy? Isn't it true that privatization encourages competition and quality of products or services and even knowledge as well as scientific development like what we saw in vaccine production recently?
Yeah, certainly. These are old issues. Privatization and animal spirits can improve the process of invention, innovation, and diffusion. There's no doubt about it. But it will depend on which industry, which product they are involved. Now, if the gains cannot be privatized, if it cannot be converted into profits, then they will not be very keen. Like some of the old diseases, like the tropical kind of problems. Multinational companies are not interested in investing. Tuberculosis, for example, because it's not very rewarding for them. But those problems are even now very, very severe, very important problems. But not many companies are interested in research. So it will depend. If there is profit available, and if that can be privatized, private capital will be interested in research. But unfortunately, there are a large number of areas where the gains cannot be privatized. So research will have to be undertaken by public institutions.
So I have a question. See, there are a lot of Keralites working, I mean, outside, working abroad, and most of them are actually wanted to come back to India and work in India or in Kerala in general. But as a member of planning board, especially, you had some idea about what we can do in that case for them. Lot of
Yeah, in fact, I should correct you. I am not a member of the planning board currently.
Previous.
I used to be there till recently, but I am now a professor at Center for Urban Studies. Now, I can tell you that we should be able to augment opportunities for absorbing such researchers here. Our universities can certainly have more positions. We have not been creating enough positions in universities, and many of our departments are lagging. And there are new areas where we need faculty. And somehow we have been, as I was telling, we were not making enough investment. And whenever we spend money, it was spent on buildings and other things. And it's very important that we invest on faculty recruitment. That's one thing. Two, of course, now we can have, the government can, already they have announced something which will attract scholars for temporary fellowships. And some of them, they may not want to come and stay back here. They may want to come and spend time here, and that can be facilitated. Apart from that, we should be able to really absorb more people.
Right.
In the coming years, we should be making investment. Our government's priorities will have to be reoriented towards knowledge generation, universities and higher education institutions.
Correct. Yeah, thank you so much. Maybe we can move to word of thanks.
Let me invite Engineer Anish Kini, scientist, KCST NATPAC, to deliver the vote of thanks. Over to you, Anish.
I hope I am audible.
Yes.
Yes.
Good afternoon to Dr. K.N. Harilal, colleagues and participants from other institutes in academia. It is indeed a pleasure and privilege to become part of 34th Kerala Science Congress, and in particular to be part of this memorial lecture giving tribute to Dr. P.K. Gopalakrishnan. I would like to straightaway go to the task entrusted. Firstly, let me place on record the deep sense of gratitude towards the distinguished speaker, Dr. K.N. Harilal, for having delivered the commemorative lecture. Sir, you have rightly articulated that economy is not just about growth and productivity, but the knowledge economy should be all-inclusive in the social realm, as well as sustainable in the long run. On behalf of KCST and the organizing committee, let me thank you for taking the time and energy to enlighten us with your words of wisdom. Thank you, sir. I would also like to thank Dr. Lata for her presence in this memorial lecture dedicated to Dr. P.K. Let me also sincerely thank Dr. C. Arunan, Principal Scientist, KCST, for welcoming and introducing the speaker. Thank you, sir. Not the least, I would like to take this opportunity to thank the August gathering for the patient hearing and interaction. I would also like to thank all those who are working behind the scenes for the successful conduct of this event. Thank you, everyone.
Thank you, Professor Harilal.
Thank you.
Thank you. Bye-bye.
Thank you, everyone.
Thank you.
End of the program. Tomorrow we will have the PT Bhaskar Panikar Memorial Lecture at 9:15. Thank you all for joining us today. Bye.